All right, so last time we started into optics and learned about polarization. And we talked about the law of Malus. And the law of Malus says that the intensity of light, which makes it through a polarizer, is given by the original starting intensity of the light times the square of the cosine of the angle between the incoming light and the polarizing angle. And so just as an example, we may have something like this. Light, let's say the light starts polarized upwards, and then I'm going to send this light through a series of polarizers. Let's say the first one is polarized at, let's say, 60 degrees. Then the second one is at 45 degrees. And the last one is at 60 degrees again. So that's our system. Light initially polarized upwards, so his initial polarization is at 90 degrees. And I'm going to try to send that light first through a polarizer, which is at 60 degrees. So the intensity that gets through this system is the starting intensity. Well, I'm not given a number for that, so let's just call it I naught, whatever that happens to be. And so I try to go through my first polarizer. That gives me a cosine squared. And what's the angle? Remember, this angle theta is the difference between what is your angle currently and what are you trying to get through. So I start at 90 degrees because I'm upwards, and I'm trying to get through a 60 degree polarizer, so 90 minus 60 gives me 30. Now, once I've gotten through that, I'm now light, which is at 60 degrees, and I'm going to try to get through this 45 degree polarizer. So again, I'm going to get another cosine squared because I'm going through another polarizer. Now this guy's angle, I'm at 60, and I'm trying to get through 45, so 60 minus 45, that gives me 15. So now I'm through this guy, I'm now at 45 degrees, and I'm trying to get through the 60 degree, so again, I'm trying to go through a polarizer, I get another cosine squared. The angle, I'm going from 45, trying to get to 60, so 45 minus 60, that's 15 degrees. Notice I never care if it's a negative angle or a positive angle. Since we're using cosines and cosine squareds, negative angles and positive angles are the same thing, so it doesn't matter about negatives. So just leave the angles as positive. And so the final answer is just going to be whatever this is in my calculator. So I naught times 0.652. Now, for anybody wondering how do I input this stuff in a calculator, there's different ways you can do it. One way is to realize, of course, when you say cosine squared of 30, what that means is cosine of 30, this whole thing is squared. So don't think cosine squared is like cosine times it's not cosine of 30. That's not what this means. Definitely not this. Cosine squared of 30 means you take the cosine of 30, you get a number, and you square that number. So either you do cosine of 30, then you square it, then times cosine of 15, then you square it, then times cosine, things like that. Another way you can do it is plug it into your calculator. You say cosine 30 times cosine 30, get an answer, then times cosine 15, then times cosine 15, then times cosine 15, and times cosine 15. So do it individually. You don't have to do the square button. Just multiply it by itself multiple times. And the last way you can do it is, if you notice, you got cosine squared 30, cosine squared 15, and cosine squared 15. What you could do is take cosine 30 times cosine 15, then times cosine 15, and you get a number. And then when you get that number, you take that number and you square that. That also gives you the same answer. So, personally, I've found many people, including myself, when you try to stick all the numbers into your calculator all at once, things tend to mess up. So, when I'm plugging this in my calculator, I just do kind of one number at a time, get an answer, and then take that answer and multiply by the next number. Get that answer, multiply by the next number, and so forth. That will limit kind of the mistakes that can happen because of parentheses and all sorts of stuff. But anyway, that was polarization. That was the law of malice. Today, we're moving on to a new topic called refraction. Now, refraction is a phenomenon of light where if you try to send light from one medium into another. So for instance, let's say we have the surface of a pond here, and down here we have water, up here we have air, and I send a light beam in, and it hits the surface of this water. Well, we already know light, of course, travels in straight lines, and it travels at constant velocity. However, when we say it travels at constant velocity, that is the speed of light, 3 times 10 to the 8th, we mean specifically it travels at that speed when it's in the air, or in a vacuum. However, once you send light through a different medium, like water, or glass, or coffee, or whatever, the water will travel at a different velocity in that medium. Now, whatever that velocity is, it's called the speed of light in that medium. So in air, it's always 3 times 10 to the 8th, and in water, it's always whatever it is, some number. It's not the same as 3 times 10 to the 8th, but it's something else. Now, because of this, what's going to happen, the phenomenon of refraction, is when this light changes its velocity in going from one medium to another, its path changes as well. So, for instance, the light does not just continue to go straight in, like that. Instead, what's going to happen is the light's going to bend and go at a slightly different path. Now, how do you visualize this? Why does this happen? And the thing I like to remember, because most people have, of course, experienced this kind of a thing. If you're driving in a car, here's the car with the wheels. Let's say the car is driving this way, forward. And it had rained earlier in the day, so there's kind of a puddle on the side of the road over here. When your car hits this puddle, notice only the right side of the car is hitting the puddle. The left side isn't, because, of course, the puddle's on the side of the road. Well, if you've ever experienced this, you know exactly what happens. If you're not holding onto your steering wheel, the car is going to careen off the side of the road. What's going to happen is, the car, as it drives, it hits the puddle and the car curves to the right. You say, well, why does that happen? It's quite simple. When these right side tires hit the water, they slow down. It's harder for the tires to move or travel through water, whereas the left side tires, they just keep going at their normal speed on the road. That's fine. They don't slow down, but your right side ones do. So if your right wheels are going slower than your left wheels, then your left wheel goes further than your right one can, and so your car curves to the right. Well, we can kind of visualize the same type of thing happening over here with the light going from air to water. When the light beam is coming in, it's going in the air, so it's traveling at 3 times 10 to the 8th, and then it hits the surface of the water. Light slows down when it hits water. It doesn't go as fast. And so the same kind of a thing happens. The light bends towards the water because it kind of slows down if you want to imagine it that way. And so what that means is the angle coming in, call it theta 1, is going to be different than the angle going out, theta 2. And this bending of the light to a new path is what is called refraction. So refraction, basically the bending of light. And it happens when you go from one medium to another because each medium has its own speed for light. And so questions we may be able to ask for this are things like, okay, well, if I send light at a particular angle and it hits the surface of the pond, at what angle will the light travel in the pond? Basically this kind of a picture. Well, to solve problems like this, we use what's called Snell's Law. And Snell's Law says this. It's very easy to remember. N1 sine theta 1 is N2 sine theta 2. So, of course, we need to figure out what these terms mean. Let me redraw the picture. Let's say we have light coming in. And then this dashed line I'm drawing is called the normal line. And if you remember from first semester physics, normal in physics and math doesn't mean regular or some psychological thing. It means perpendicular. So the normal line is the line that's perpendicular to the surface of this water. So up here we have the air, down here we have the water. And we have some angle. Let's say the light's coming in at 30 degrees. The question is, what will the angle be in the water? Call it theta 2. Or another way of asking is, what is the angle of refraction? So in this case, theta 2, which is the angle in the new medium, is also called the angle of refraction. So for a problem like this, we use Snell's Law. So we need to know, what are these terms? Well, N is called the index of refraction. And all the index of refraction is a characteristic of the medium that tells you basically what's the speed of light in this medium. Now, it's not exactly the speed of light, it's a ratio, and the ratio is the speed of light in a vacuum, c, divided by the speed of light in the medium. So the c on top is 3 times 10 to the 8th meters per second. And the v is the speed in this medium. So for instance, maybe in water it's 1 times 10 to the 8th. And in glass, maybe it's 2 times 10 to the 8th or something. So the velocity in this new medium is v, and the velocity in air or in vacuum is 3 times 10 to the 8th, the constant. And so what you're going to find is the index of refraction for a material is always some number bigger than 1. And that's, of course, because the biggest v can ever get is 3 times 10 to the 8th. That is the speed of light in a vacuum. That's as fast as it ever goes. So the biggest number this can ever get is 1. Or I'm sorry, the smallest it can ever get is 1. My apologies. Because v can never get bigger than c. Now v could be less than c. As I said, when light goes into water, the speed slows down. So if v is a number less than c, then c over v is some number bigger than 1. Now, you're going to need to know 3. Of course, I'll probably put these on the test, but just so you can have them to work with easily, N for air, that's just 1, because it's c over c. N for water, that's 1.33. And N for glass we're going to use 1.5. Now obviously these are slightly simplistic numbers because there's different forms of glass, glass made of different materials. There could be salt water or fresh water. Temperature can affect things, but for our business here, these are going to be the numbers we use. So, if we know the index of refraction for the materials, we know the angle of incidence, we can solve this problem. We'd say, okay, for our particular problem, if you remember what it is, light traveling in air is incident upon the surface of the water at an angle of 30 degrees with respect to the normal. So these thetas, theta 1 and theta 2 in Snell's law, those are always the angles with respect to the normal, not with respect to the horizontal. So light's incident on the surface of the water at an angle of 30 degrees. Calculate, let's say, calculate the angle of refraction. It's the same as saying, what is the angle that the light travels in the water? Well, we want to use Snell's law. So we'd say, okay, N1 sine theta 1 is N2 sine theta 2. So we're starting in air, so our 1 stuff is air and our 2 stuff is the water. We're going from air to water. So index of refraction for air, that's 1, times the sine of the angle in the air, well, we're coming in at 30 degrees, must be N2, that's the index of refraction in the medium we're going to, which in this case is water, so that's 1.33, sine of theta 2, where theta 2 is the angle I'm looking for. So all I have to do is solve this problem for theta 2. So how do I do it? Well, get sine of theta 2 by itself, so I divide the 1.33 over. So you get 1 times sine of 30 over 1.33 equals sine of theta 2. And now we say, well, that's fine, but I don't want sine of theta 2. What I want is theta 2 by itself. So how do you get theta 2 out of this function? Well, instead of taking the sine of theta 2, we do what's called the inverse sine. So you take the inverse sine of that, but if you do it on the right, you also have to do it on the left, so we take the inverse sine of all of this. And when you do that, the inverse sine cancels the sine, and so you're left with theta 2 equals, and now on the right, we have inverse sine of sine of 30 over 1.33. And so you stick this in your calculator, and you get theta 2 is 22.1 degrees. And this makes sense, because if you remember, we started at 30. I'm going into a more dense region, that is, water is more dense, the velocity slows down, my angle should get smaller, and indeed, my angle goes down to 22 degrees. So perfect. Now, going further with this, there's another thing we need to understand, and this is the phenomenon of the critical angle. Now, critical angle, it's completely related to refraction and Snell's law, and it goes like this. Let's say, instead of going from the air to the water, I'm going from the water to the air. So again, here's my little normal line. Well, if I'm going from the water to the air, when my light hits the surface, the angle should get bigger. But let's follow this. Let's make a bigger angle coming in. Well, now, of course, this gets closer and closer to the horizontal. And if you notice, there's eventually going to be an angle that if I hit it at this angle, the line skims the surface. And in fact, any line with an angle greater than this, it actually comes back down again. So this special line right here, this red one, whereby the angle of the incident light makes a refraction where the light doesn't come out of the water, but it skims the surface of the water, this is the critical angle. And what is a critical angle? It's this angle of incidence that makes this happen. Okay? This is a very special angle. And as I said, any angle below it, like the gray and the black lines, the light comes out as normal. Any angle bigger than it, like the green line, the light actually reflects back into the water. It does not go into the air. So, if you're in a swimming pool, for instance, and you have a laser pointer, let's say the swimming pool surface is very, very smooth, not rough and choppy. Well, someone's standing outside of your swimming pool looking down towards you, there's a certain angle and any angle above it that you could shine this laser pointer and they'll never see the laser come out of the water because the surface of the water acts like a mirror and it reflects the laser back down into the water. Now, this is a very, very important phenomenon. It's what allows for fiber optics. If you've ever heard of fiber optics, a lot of things use it. It's basically a wire that sends data signals in general. You know, for instance, a lot of stereo systems in the past used, and still do today, use fiber optics to send the data, the sound data, and so forth. Of course, you see a lot of decorations use fiber optics just purely as a means of making light come out of the little glass fibers. But what's happening is light is sent into this wire at a very specific angle. And so the light, instead of trying to come out of, and what I've drawn here, this tube-looking thing, imagine it being glass, completely transparent. But because it's coming in at a very special angle, the critical angle, or usually above that, then the light actually reflects back into the tube and just keeps going, reflecting back over and over again as it travels down the wire. Until, of course, you get to the end where it releases the data, releases the light. And if this is like a tabletop Christmas tree, you see the sparkly light coming out of the ends, but you don't see the light throughout the glass fibers. You only see it at the tips. And that's because the light is stuck reflecting inside of this glass until it reaches the end. So it's a very useful concept, and this phenomenon occurs, of course, in any medium. The key, of course, is this only works when you're going from a more dense region to a less dense region, or sometimes called rare region. So, for instance, if you go from water to air, you can have a critical angle. But if you try to go from air to water, you cannot have a critical angle. You only get critical angle type stuff when you're going from more dense to more rare regions. Water to air. Glass to water. Glass to air. That works. Air to glass, no. That doesn't work for critical angle. So, the reason I bring this up is because we can ask, what is the critical angle for water? Can we figure this out? And indeed we can. We have all the information we need. Well, critical angle for water, that is, I'm going from the water, I hit the surface of the water-air barrier, and what do I know? I know the light skims the surface. And so what is it I'm looking for? I want to know what is this angle here, call it theta C, the critical angle, such that this is true. So here's the water side, here's the air side. Now, what you're going to find if you look this up online, other textbooks and things, you may see a very specific formula to use to get critical angle. I don't recommend it only because you don't need to memorize a new formula. Snell's Law works. So we'll use Snell's Law, and it says n1 sine theta 1 is n2 sine theta 2. Now, for our discussion, what are the ones and what are the twos? I'm starting in the water and I'm going from air. So water is 1, air is 2. So we say, okay, and 1, that's water's index of refraction, 1.33. Sine of theta 1, what's theta 1? That's the angle in the water. That's what I'm looking for, so I call it theta c. All right, now I need the air stuff. Index of refraction for air is 1. Sine of theta 2, what's theta 2? Well, theta 2 is the angle in the air. So, from the normal line to where the light is in the air, if you notice, it's this angle right here, which is 90 degrees. So, theta 2 is 90. And in fact, every time you do critical angle, theta 2 is always going to be 90 degrees. That's the definition of the critical angle. The critical angle is the angle of incidence, which makes the angle of refraction 90 degrees. All right, so here's our equation. I need to solve this for theta c. So, okay, get sine theta c by itself. Sine theta c equals 1 times sine of 90 over 1.33. Again, we just want theta c, so I take the inverse sine of both sides. So theta c equals inverse sine of sine of 90 is just 1. So this is 1 over 1.33. And you get 48.75 degrees. Now, when I said before, textbooks and stuff will show you a different equation. What they'll show you is this equation. As a shortcut, theta c is inverse sine of n2 over n1. So if you look, air was our n2, that's 1. Water is our n1, that's 1.3. That's how we got our answer. But notice this didn't just come from nowhere, it comes from Snell's Law. And it's been my experience in the past that if students learn how to do critical angle from Snell's Law, they get a much better practice for all of the refraction problems, not just for critical angle, than if they try to memorize critical angle as its own equation and Snell's Law as something else. They're not two different things. The critical angle formula that I've drawn in gray on the left is Snell's Law, where theta 2 is always 90 degrees. And they just manipulate it down and get it as simplified as possible. What you're going to see on the formula sheet is Snell's Law. I do not have the critical angle formula on there because I'm advising you. Use Snell's Law to solve all your refraction problems. Whether it's angle of refraction or critical angle, doesn't matter. Always use Snell's Law, and you can get what you need. All you have to do for critical angle is remember that the critical angle means when you're trying to go through to the second medium, the angle in the second medium is 90 degrees. It skims the surface. All right, so that's refraction. I'll see you next time.